Okay, this is translational body motion, whatever, and we'll be finding the acceleration of a toilet paper as it falls, and I'm holding it. It's not gonna cause a drag, but it's gonna cause it to slow down because I'm kind of pulling it up a bit, and so we'll be finding that. I guess some background, not necessarily for spinning things, right? But let's say you have like a little wheel, and if you apply a force to this, let's say that's R, or let's call it D. That's going to cause a torque on the axis called a F, which that torque is going to be equal to the force times D. However, the force has to be perpendicular to the axis of rotation. So if it's like pointing this way, since it's parallel to the axis, it's not going to do anything for torque. So it has to be perpendicular, and sometimes you can get like some weird angle like that, so you have to find that horizontal or that perpendicular component. And when you have spinning things, the torque is also equal to the moment of inertia of that object times the angular acceleration. And so depending if that thing is spinning clockwise, it's negative, and if it's going counterclockwise, it's positive. You can also rewrite this angular acceleration from the formula sheet as A over whatever R that is. And that will be using those concepts to solve for this little guy right here. Okay, so the inertia, the small r, is the radius from the center to the outer or the inner rim, and then the big R is the center to the outer rim, or essentially small r, big R. And then the way I'm solving it, you can use energy, but the way I'm solving is that we're going to just use torque. And so you could either assume it's rotating about the center and ignore mg, or it's rotating about point, or the tension point right here, where I'm grabbing the toilet paper roll, and ignore this tension. For the sake of using the parallel axis theorem, I'll find it about here. Okay, let's write down what we know, or that's just essentially this, and then we're going to find the moment of inertia about this point right here. So to do that, we have to use the parallel axis theorem, which is just, right? So that's just a formula. And then the I center of mass is just this, so you can just plug that in there. And then D is going to be the point where the center of mass was to the point where you want to find it now, which is just big R. So we'll replace all those. It's going to be like that. And then, just to simplify this, Alright, and then this is our new moment of inertia about point, I guess we could just call this T. Okay, now we have this, and so now we do the sum of the torques, which will be, I just like writing that. We're at point rotations at point T, so this force is not going to have any torque on it because it's at the point of rotation, so there's no R. And then our second force is mg, which is a distance r, so that's the only force acting on this. It's making it move clockwise, so this force is going to make the object move clockwise about this point. It's going to be negative, is moving also clockwise, it's negative. You plug this into here. This is all positive, by the way. There you go. M's cancel out. Let's isolate this alpha. Angular acceleration alpha is also equal to linear acceleration over the radius, so big R in this case because it's like the total radius of the object. Solve for the linear acceleration of the object falling. We just multiply both sides by R, so it's going to be R squared, and then this goes away. So
A is going to be 2gr squared over little r squared plus 3r squared.
That's going to be it. By the way, I didn't put the answer. This is, the inner radius is 2 centimeters, the outer radius is 6. Then also for the example, I'm assuming when it's falling down, the acceleration is positive, so mg is positive, tension is negative. That's how I did it. My voice cracked, and I think we should do the experiment now. And if you're curious, if you take the moment of inertia or the point of rotation about the center and not about this point, you don't need to use the parallel axis theorem, but you do need to solve for t in terms of g and a. And then if you do algebra for this, solve for a, you get the same thing.
One more moment. Oh, look. Since the last video, I might as well let my hair down. Go this way this time. Over height that is. Is that bigger?
And finally, from the video you probably just watched, it was recorded at 60 frames per second. It took 36 frames for the toilet paper to hit the ground from holding it. Therefore, the time it takes is 36 over 60.6 seconds. Using the position kinematic equation, there's no initial velocity, so it's just h minus 1/2 at squared. Solve for a, and the initial height where it was dropped from was 1.25 meters, about 4.1 feet, I believe. And so A experimental is 6.9 meters per second squared, and A theoretical, the one we calculated, was 6.3 meters per second squared. And so the percent error of that, I believe, is 9%, but I think that's pretty good for just a one-try thing. Whatever. Peace.